Morning, everyone. We're going to get started here. So we left off talking about calculating molar masses for compounds. So to review this sort of mishmash flow chart here, we've got two different branches going on with this flow chart. The top one here has to do with a compound. The bottom one has to do with elements. And then, we can even add on top here as far as like differentiating each of these sections. For everything that's here, this is talking about mass. This over here is talking about moles in both instances. Right? And then this over here is talking about particles. So we've got sort of 6 quadrants. Anytime we're going from particles to moles, doesn't matter if it's a compound or if it's an element, we use Avogadro's number. Anytime we're going between mass and mole, this is where we need to use the molar mass, which if it's an element, we pull it off the periodic chart. If it's a compound, we pull the masses of each element, and then we need to calculate it by multiplying by the subscripts or how many we have. So I'm going to give you a couple compounds, and I want you to tell me what their molar mass is. So let's do iron 3 hydroxide. That would be FeOH3. Let's do aluminum sulfate, Al2SO4 3. And then let's do calcium carbonate, CaCO3. Okay. I want you to find the molar mass for each compound. All right, so I had to go run and get my daughter's periodic chart. It's one of those like placemats that you have at the table. You can get them at Michael's. It's actually really awesome because you can learn your elements while you're having your dinner. So, and keep your table protected. Okay. So when we're doing a compound, there's an extra step of having to add these things together. So iron has a mass of what, 55.85 roughly. And there's one of them, so we're gonna just multiply it by 1. Oxygen is 16, and we need to multiply it by 3. You know, I'm gonna put these in parentheses because I don't want those dots getting confused. Because the 3 distributes out to everything within the parentheses. And then we've got hydrogen, which is roughly 1.01, and we multiply also that by 3. And then we have to add these things together. So the total here, 106.87. And if you're wondering what are the units on this, the units are grams per mole, right? It's a molar mass. Specifically, it's grams of iron 3 hydroxide for every mole of iron 3 hydroxide. If you got 106.86 or you got 106.84, that's okay. That's close enough. It'll get you the calculations you need. Every periodic chart is sort of rounded off a little differently. So don't stress too much about, you know, that hundredths place. Now, if you had 80, you know, or I'm sorry, if you had 108 or 107, well, even 107, I guess would be okay, but 108, anything where you're starting to get a number off in the ones place, you're going to want to recalculate. So the next one, we've got aluminum, which is 26.98, and we're going to multiply that by 2. Sulfur, which is what, 32.07 times 3. Because again, the 3 gets distributed to everything. And then oxygen is 16, and we're going to actually multiply that by 12. All right, because there's 4 within the parentheses, there's 4 within each polyatomic, and you have 3 polyatomics. So you want to make sure you're multiplying subscripts if there's more than one, or if there's one within the parentheses and one without. And so this has a pretty decent size molar mass. 342.15. And again, the unit on that, gram per mole, specifically a gram of aluminum sulfate per mole of aluminum sulfate. The last one here is calcium carbonate. So we've got 1 calcium. Calcium is 40.08. We're going to multiply that by 1. Carbon is 12.01 or 12.0011. We're going to also multiply that by 1. And then oxygen, which is 16, we're going to multiply that by 3. And when we add those together, we should get almost exactly on the nail 100. I'm going to give it 2 decimals, 100.09 grams per mole. Are you feeling okay with how to calculate those? Like where those numbers are coming from, why here it's 12, right? The 3 times the 4. Okay, if you do have any questions on that, speak up. So now we've been able to get our like intermittent, right? Or we know how to calculate our conversion factor between these two. So let's solve for a problem. And let's use one that we already calculated. All right, so given, let's say how many moles are in 1.52 kilograms of Al2SO4 3. Now note, I gave you value in kilogram, so just make sure you're converting when needed. I'll give you 2 minutes or so. Because we're dealing with aluminum sulfate, you can use molar mass here for this guy. Okay, so in this problem, we're talking about a compound. So on that master flow chart, we want to be in the compound section. So if we're going from grams into moles or moles into grams, we need to be using a molar mass. So I'm going to write the molar mass just here. So molar mass for this guy is 342.15 grams for every 1 mole. That's unique to this problem. Right? Now, a couple things that are really one thing you want to note, the unit was given in kilogram. I see that happen quite often where people will skip over and they'll say, oh, kilogram, whatever, it's a mass thing. It's pretty much the same thing as a gram, isn't it? It's not. You've got to make sure you're in grams. You can't use a molar mass if your unit isn't in gram or in mole. Right? This is not kilograms per mole, it's gram per mole. So we got to match up before we can convert. There's 2 ways you can convert. You can use King Henry died before drinking chocolate milk and just move the decimal over 3 places. Or you can put it into dimensional analysis. I'll do that. 100 or 1.52 kilograms of the Al2SO4 3. If I want to convert this into grams, well, for every 1 kilogram, I get 1,000 grams. Right? And the unit of kilogram will cancel. And this is specifically grams of Al2, SO4, 3. Same thing as moving the decimal over 1, 2, 3 halves. So it should be 1,520 grams. So now we need to go into the next step, which says, hey, how many moles do we have? So if gram is on the top here, I want to get rid of gram. So I'm going to put gram of Al2, SO4, 3 on the bottom, and I'm going to put the mole of Al2, SO4, 3 on the top. What is the relationship between these two? It's the molar mass. So for every 1 mole of this thing, I get 342.15 grams. The number always goes with the gram. This will always be grouped together. What does the mole get? The mole gets a 1. So we have 3 sig figs. So when I round it out, I should get 4.44. 4.44 moles of Al2SO4, 3. So just like with the elements, can you do a multi-step? This problem had you just go from grams to moles, but could you be given grams and go to number of atoms, or number of atoms and go to grams? Definitely, right? We can hop through multiple steps here. So let's do that. How much does, how much does 8.325 times 10 to the 26th calcium carbonate molecules weigh in grams? Okay, so how much does 8.325 times 10 to the 26 calcium carbonate molecules weigh in grams? So I'm going to give y'all, you should have the molar mass already calculated. So I'm just going to give you 2 minutes for that one. Okay, so when you're given a problem like this, I guess first thing you ask yourself, is it talking about an element or is it talking about a compound? So in this case, it's talking about a compound. So we're going to want to go up here. We are given the number of molecules. We want to figure out grams. So we should take 2 hops. We're going to take molecules into moles, moles into grams. The additional step when we're dealing with a compound is we need the molar mass of the compound. And we actually calculated that right here. So we can just sort of pick that from there. So if we're going from molecules, we got to first go to moles. There's no way to go directly from molecules to elements. Moles is our chemistry crossroad. So 8.325 times 10 to the 26 CaCO3 molecules. That's what we're starting with. I want to get rid of molecules. So the CaCO3 molecule is going to go on the bottom, and I want to get into moles. I mean, yes, at the end of the day, I want to get into grams, but first I need to get into moles. So how do these relate to each other? Well, remember, 1 mole of anything is equal to 6.022 times 10 to the 23rd individual particles. That's Avogadro's number, Avos. So that'll get us through step 1. The second step is to use the molar mass to get us from moles into grams. Now in this first hop here, we had moles on top. Now we want to put the mole on the bottom because we don't want to see mole anymore. So moles of CaCO3 on the bottom, we want to see grams. That's where we're headed. Well, 1 mole of calcium carbonate weighs roughly 100 or 100.08 grams. Okay. Molecules will cancel out and moles will cancel out. So in this process, we will take our first number, our given information, we multiply it by a 1 and we multiply it by the molar mass of 100.08. Then we divide it by anything that's underneath these fraction bars. The only thing really, we don't have to divide by 1. The only thing we really need to divide by is that Avogadro's number. So again, when plugging these into your calculator, if you have an exponent on the bottom, you need to put it in parentheses like this, or you need to use the EE. So we actually got a pretty decent number here, size-wise. I've got when I ran this through my calculator, I got 138,353 grams of CaCO3. And then I'm going to refine it by using the sig figs that were given to me. So 1, 2, 3, 4 sig figs. So that means we get to keep the 1, we get to keep the 3, the 8, and this 3. The 5 will tell the 3 to round up to 4. So it's 1, 3, 8, 4, and then the other spots will fill in with a 0 grams of CaCO3. Now, if I want to take this another step further and write it in scientific notation, because this is kind of a large number, it can get a little cumbersome, move the decimal place over 1.384 times 10 to the 10 to the 5th grams of CaCO3. So similar process to what we were doing last time with the elements and converting between grams and atoms. We just have that extra step of needing the molar mass of the compound. Any questions on that? Okay, because what we're going to do now is we're going to tie these 2 limbs together of our flow chart. So we're going to start taking compound and element and relating them to each other. So this over here, you guys already probably feel somewhat comfortable with this. Hold on. Ants are everywhere now. They're starting to come in my house. This right here, atoms within an element and molecules. These relate to each other by the subscript. or let's say formula subscript. So if I have a molecule, like let's say I have H2O, how many atoms are in that element? Well, you can look at the formula and you can see, hey, there's 2 hydrogens and there's 1 oxygen. So there's a way to relate to each other. This idea of the formula subscript also applies over here. So how do we relate a mole of a compound to a mole of an element? We also use formula subscripts. And I will show you a little bit more on that. So for now, just fill that in. Over here, you see where it says gram of compound to gram of element? Put like an X or something. You cannot go directly between those two, okay? So if I have 55 grams of sodium chloride, I cannot directly get the grams of the element. I will have to move in a different way on the flow chart. So no direct way between those two. These two are connected by formula units. So let's look into that a little bit more. All right, we're good with that. So we're going to talk about a clover. So if you have a clover, you should have 3 leaves. Sometimes you can get 4 leaves or 5 leaves, but in general, usually you get 3 leaves. So 1 clover will yield 3 leaves. So if I have 14 clovers, how many leaves would I have in total? You may be thinking, well, obviously you're just going to multiply 14 by 3. If we were to set it up in dimensional analysis, though, this would be our relationship between the whole and the individual, right? So the whole thing is the clover. This is the whole. And then this over here is the individual. So 1 clover yields 3 leaves. If we have 14 clovers or 14 of the wholes, and I want to figure out how many individual things I have, I'm going to put the clover on the bottom and it'll yield 3 leaves, or 14 times 3, which will give us a total of 42 leaves. This is what's happening when we're trying to go from a compound to an element. Like if I have 15 moles of aluminum oxide and I want to know how many moles of oxide there or oxygen there are, I can relate them using the formula script. So when looking at a formula unit, excuse me. Ooh. Something in my nose. Like CO2, for instance, okay? For every 1 molecule of CO2, how many atoms of oxygen do we get? We get 2 oxygen atoms, right? It's really easy to read right off the bat. So 1 molecule of CO2 will yield 2 oxygen atoms. Another thing, 1 molecule of CO2 will yield 1 carbon atom. Similarly, let's say instead of having 1 CO2 molecule, I had a dozen CO2 molecules. Well, if I had a dozen CO2 molecules, I should have 2 dozen oxygen atoms, right? Because there are 2 of these for every 1 of these. The same thing is true if we go to our chemist's dozen or our dozen on steroids. If we have 1 mole of CO2, or I have 6.022 times 10 to the 23rd molecules of CO2, I should end up with 2 moles of oxygen. Similarly, if I have 1 mole of CO2, I should get just 1 mole of carbon. So now hopefully you're starting to see how this formula is a recipe, right? It tells you how much of each thing you need. And if I know the moles of my element, or I'm sorry, the moles of my compound, I can really easily jump into moles of the element. Important thing is that these formulas, whatever it happens to be, CO2, H2O, C6, H55O11, all of those are molar relationships or mole relationships, okay? So give yourself a note somewhere. I'll write it down on our other page over here. make some space. So give yourself a note that says formulas for a compound are mole relationships. And then if you want to put in parentheses here, you can say not mass. Okay, it's not a mass relationship, it's a mole relationship. So when I see H2O, this is saying that 1 mole of water needs or uses 2 moles of hydrogen and 1 mole of oxygen. It's a mole relationship. These numbers are letting us know how many moles of each thing we need. It's not saying a gram relationship. A lot of times people will see this and say, oh, it means that it's 2 grams of hydrogen for every 1 gram of oxygen. No, 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 no. Okay. Because of the fact that these are mole relationships, that is why you can't do a direct hop between, like if I give you the amount of a compound and I want you to tell me how many of the element are within there, like you have 15 grams of water, how much of that is hydrogen? You can't do a direct relationship. The formula tells us a mole relationship. So first we need to go from grams of the compound into moles of the compound. Then we can use the formula unit to get to the element and then go back to grams. So this would be a 1, 2, 3 step problem in order to do that. We'll practice that. But for now, right, formula units are telling us a mole relationship. So I want you to give me all the possible molar relationships. Well, let me show you one. Let me do it for the water first. So we know that 1 mole of water produces 2 moles of hydrogen and 1 mole of oxygen. So some things I can do is I can write a couple conversion factors. This I could relate to this. So I could say 1 mole of H2O will yield 2 moles of hydrogen, right? Or I could write it 2 moles of hydrogen will yield 1 mole of water. Which one you use is really dependent on the direction you're going in the problem. Another relationship I have here is this one. 1 mole of water needs 1 mole of oxygen. So 1 mole of water yields 1 mole of oxygen, or 1 mole of oxygen can produce 1 mole of water. So there's all these built-in conversion factors from this formula by looking at the subscripts. I could even relate water and hydrogen to, oxygen and hydrogen to each other by going, let's use a different color, blue, here to here. I could say, hey, in order to make a water molecule, I need 2 moles of hydrogen, or 2 moles of hydrogen need to combine with 1 mole of oxygen, or 1 mole of oxygen for 2 moles of hydrogen. So now there's all these built-in conversion factors. So I want you to write a couple conversion factors for this formula. What do I want to do? Ca, I'm going to give you something a little tricky. Ca3, PO4, 2. Okay. So I want you to tell me, what are the mole relationships between all the elements? I know that this here is a polyatomic ion, but just tell me the relationship between a mole of the molecule and how much calcium, how much phosphorus, and how much oxygen it yields. And if you want to go a step further, you can write a couple, you don't have to write every conversion factor, but you could write a couple conversion factors. Okay, so some of the relationships here are if you have 1 mole of the compound, and usually when you're doing these relationships, you assume that you have 1 mole of the compound. Okay, so 1 mole of Ca3, PO4, 2. How much calcium is in 1 mole of this? It should be 3 moles of calcium. So that's a relationship between moles of the compound and moles of calcium. I could actually hop between those two really easily. What's another relationship? If I have 1 mole of this compound, how many moles of phosphorus do I have? 2 moles of phosphorus. All right, the 2 is getting distributed to both of them. And then 1 mole of this compound will yield how much oxygen? Well, there's 4 within and then 2 on the outside. So that's a total of 8. 8 moles of oxygen built into every 1 mole of the compound. So now we have 3 conversion factors that we can use in either direction. Which one you use is really dependent on what the problem asks. So let's say, how many moles of oxygen are in 17.4 moles of Ca3PO4, 2. So same formula as this one right here. So you'll be using one of these conversion factors. I want you to give it a try. You're going from the compound to oxygen. Okay, so of these built-in relationships, and you know, as you get more comfortable, you're not going to have to like actually write all these out. You'll just be able to look at the formula and say, oh, the relationship between oxygen and the molecule is 8:1. But we are going to use this one here because it relates the compound to the amount of oxygen. We don't have to worry about phosphorus or calcium. The problem isn't asking about that, so we don't need that. So we start with our given information. We have 17.4 moles of Ca3PO4, 2. And I want to figure out, well, how much oxygen is that? So the relationship is Ca3PO4, 2 to oxygen, specifically mole of each of those. So 1 mole of the molecule will yield 8 moles of oxygen. I'm putting the oxygen on top because that's what I want to go towards. Moles of the compound cancel, and we're left with hopefully just oxygen. When I calculate it out, I get 139 moles of oxygen. You may be wondering, well, how can you start with 17 moles and now we have 139 moles? Well, we're talking about moles of different things. Right? This is a mole of a very large, clunky molecule. This is a mole of just an element, right? This is much lighter. It's like, you know, if you're talking about a dozen, are you talking about a dozen cars, which have a lot of moving parts, or are you talking about a dozen screws, right? The screws are going to be a much smaller thing. So you can have a lot of screws in just one car. So this is that step that now pulls these two limbs together. So we can go from a compound to an individual element, or I can go an element to a compound. It needs to happen though at the mole step. It could also happen at the molecule step, but I wouldn't really recommend going, like if you have grams, I wouldn't go to moles and then molecules and then atoms and then moles and then grams. That's like too many steps. You can just truncate it here. So let's try that out, because how often are you given something in moles in real life? You're not. You're usually given things in grams. So if I give you given, we have 1.79 grams of aluminum oxide. And I want to find grams of just the aluminum. This is where I'm saying you cannot go from gram to gram directly. There is no way to do that. You have to move through the flow chart in a valid way. So back up here, I am given an amount of a compound, and I'm saying, hey, how much is an amount of the individual element? So in order to do that, I need to go grams to moles to grams. And this is going to be something that we see a lot, is this flow chart of gram to mole to gram, gram to mole to gram. So I need to take my gram of compound, and I first need to convert it into moles of the compound. Then once I have moles of the compound, then I can get into moles of the element, right? That's sort of our magic step using those formula units. I've transferred from one thing to another. And, hello. Coffee everywhere. 1 second. He's answered, just driving me crazy. And then once we have mole of element, then I can convert back to grams of the element. So the flow chart is here to here to here to here. And if we do it specifically for this problem, which I will work with you guys together, and then I'll give you one on your own. But if we work this one, we need to start with grams of the compound, Al2O3. We need to first convert it into moles of the compound, Al2O3. Then we can go moles of the element, and in this case, we want to go towards moles of aluminum. Is the problem asking you anything about oxygen? No, so we can, I mean, kind of ignore oxygen, except when we're calculating the molar mass here. And then once we've got moles of aluminum, then I can convert back to grams of aluminum. And so often I have students try and figure out ways to just go from here to here. And yes, there are some ways to do it, but it is more complicated, I think. It's just easier to break it up. So filling in our arrows, which will be our conversion factors, I need a relationship between grams of aluminum oxide and moles of aluminum oxide. That's our molar mass of aluminum oxide. So go ahead and calculate the molar mass of aluminum oxide. It's going to be 2 aluminums and 3 oxygens. And if you start getting the idea of how to calculate molar mass, and you're like, my gosh, this is just so much work, more work than it's worth, because I get it, you get the concept. You can always type into your cell phone under Google, molar mass of aluminum oxide, and it will like literally just pop up for you. So after you've done like 500 of these on your Mastering Chemistry, you may want to just, you know, cheat a little bit there. So when I plug it into my phone, because I'm being lazy, the molar mass of aluminum oxide is 101.96 grams per mole. So 101.96 grams for every 1 mole. Actually, instead of using a fraction, I'm going to 6 grams for every 1 mole. And it's specifically grams of Al2O3 for every 1 mole of Al2O3. Now, this step in the middle, I always kind of call it like the magic step, because you're transitioning from one thing to another. This is not the same thing as this, right? Yes, they both, oh, let me put an L in there too. There is no element Al. Yes, they both contain aluminum, but these are not the same thing. This is aluminum oxide and this is aluminum. So whenever you're trying to transition between one thing and another, that's where you use your subscripts. So for every 1 mole of the compound, which in this case is aluminum oxide, how many moles of aluminum do we get? Well, it's right there for you. You get 2. So 2 moles of aluminum. It's built in. You don't have to like memorize them. It's just built into the formula for you. The last step then here is to go from moles of aluminum into grams of aluminum. How do we get from moles to grams or grams to moles? Again, this is using a molar mass. In this case, we only need the molar mass of what we're talking about, which is aluminum. So 26.98 grams of aluminum in every 1 mole of aluminum. So there's 2 molar masses going on. One of the molar masses is for the compound. One of the molar masses is for the element. And in the middle step, you're using the subscripts. So let's thread those together. We start with our given information, which was what, 1.79 grams? Okay, so 1.79 grams of the Al2O3. First step, I have to go from grams of the compound into moles of the compound. That's what the flow chart tells you to do, so do it. So grams need to go on the bottom because we want to get rid of that in this step. We want to get into moles of the compound. And if you've done this step here, if you've sort of made your flow chart and filled in the steps, this becomes very easy. You just take what you have here and you pull it down. So 1 mole of the compound yields 101.96 grams. Next step will be to go from moles of the compound into moles of the element. Well, the compound is up top here in moles. So that means the compound in moles needs to go on the bottom because we don't want to see the compound anymore. We want to get into just talking about aluminum. So we're going to put moles of aluminum on the top. And then what is the relationship? Well, 1 mole of the compound will yield 2 moles of the aluminum. The final step, so that got us here. The final step is just to go from moles of the compound, or rather moles of the element, into grams of the element. So I'm going to put the mole on the bottom because the mole is on the top here. So 1 mole of aluminum will weigh 26.98 grams of aluminum. And as you go through that process, right, checking that things are canceling. So grams of aluminum cancel with grams of aluminum, grams of the compound with grams of the compound, moles of the compound with moles of the compound, and then moles of the element with moles of the element. So quite a bit of steps, quite a bit of numbers to plug into your calculator, just being careful that you're using things or using your functions correctly. So we got 1.79 times 2 times 26.98, and then divide by anything that's on the bottom. The only thing on the bottom I have is that heavy molar mass, 101.96. And I end up with a number that is 0.947 grams of aluminum. The only unit left is the gram of aluminum, right? So within 1.79 grams of aluminum oxide, 0.947 grams is aluminum. Does that make sense conceptually? Yeah, we would expect one of the elements to weigh less than the total compound. So this flow chart is going to be the same anytime you're given a problem like this. So I'm going to right off the bat, while it's fresh in your mind, I'm going to give you another one just for a different compound. So let's say that we're given that you have 1.92 times 10 to the 3 grams of calcium carbonate, CaCO3, and I want you to find grams of oxygen. So I'll give you 5 minutes for that. You might want to first start by drawing out your flow chart, so just so you can start to conceptually get what you're doing and then run through the calculation. But it is very much going to mirror what we did here. It's just a different compound in a couple different relationships. So this problem differs from the last one we did together only in like what it is as far as it being calcium carbonate, but the setup is still the same. So we're going to go from grams of the compound, in this case it's CaCO3. We've got to go grams to moles to moles to grams. So grams of the compound into moles of the compound, CaCO3, into moles of the element. And in this case, we're talking about oxygen, so moles of oxygen. And then we're going to go to grams of oxygen. And then I'm going to fill in my steps here. So anytime we go from gram to mole or mole to gram, we need the molar mass. The molar mass of calcium carbonate is 100.08 grams of the calcium carbonate for every 1 mole of calcium carbonate. We calculated that earlier in class. The relationship between moles of the compound and moles of oxygen specifically, we just want to look at the oxygen. Well, it looks like we get 3 oxygens for every one molecule, right? So 1 mole of the CaCO3 is going to give us 3 oxygens. And then the last step is to go from moles of just oxygen into grams of just oxygen. So we have to use molar mass of only the oxygen. 1 mole of oxygen should yield 16 grams of oxygen. It's just the molar mass off the periodic chart. So now we can set this thing up in our dimensional analysis. Start with our given, 1.92 times 10 to the 3 grams of CaCO3. Don't get freaked out by this exponent here. You can plug it in your calculator. You can move the decimal over if you want to get rid of that. All right, so first step is this stuff here. Gram is here, so I'm going to put gram down on the bottom, CaCO3. I'm going to put mole of CaCO3 on top, and then what's the relationship? Well, 1 mole of the compound yields that 100.08 gram. Next step, so we did that. Now we want to go from the compound into the element. Well, compound is on top, so I'm going to put compound on the bottom. So 1 mole, a little more space. 1 mole of CaCO3, we already said here, yields 3 moles of the oxygen. I didn't put mole there, but that's 3 moles. That takes care of the second hop. The third hop is going from moles of oxygen into grams of oxygen. I want to get rid of mole, so I'm going to put 1 mole down at the bottom, 1 mole of oxygen, and that always weighs 16 grams. Compound gram cancels. Mole of compound cancels, mole of element cancels, and we're left just with the gram of the element. So we're going to take our first value and multiply it by 3, and then also multiply it by 16, and then divide by anything that's on the bottom. And in this case, it's that 100.08. And I get 921 grams of oxygen for my answer. So is that outside of, needing to practice and do homework and things like that, is that making sense? I think that especially in the beginning, setting it up like this so that it's kind of dummy proof is really good, right? And then you may find later on, oh, I know this system. I need to convert it to moles. And then I use the relationship between the subscripts and then I go back to grams. But for now, in the beginning, you may find that it's useful to do that extra step. So this here and this here, these little flow charts are built into that master flow chart we have. It's just kind of at an angle. It's going this way, here, down, and then back over. So you can use this flow chart in a bunch of different ways. Like I could give you grams of compound and say, I want to know how many atoms of a specific element there are, this thing over here. And I could go this way and then down and then over. Or I could go here, here and then down. I could give you the number of molecules and say how much of a certain element is there in grams. So you start here and you want to get down here, and you could go over, down, and over. There's a bunch of different ways to use this thing, right? The only place that doesn't have a connector, I mean, we don't connect on diagonals, okay? We don't connect directly here. So we can't do anything gram to gram. We have to move on to another part. So, these slides are kind of just going through what we already talked about. It says here, you know, hey, if you have 15 grams of sodium chloride, how many grams of just sodium is that, right? You're taking the grams of the sodium chloride, going into moles of the sodium chloride, going into moles of sodium, and grams of sodium. Same thing, grams to moles to grams. You see that happen over and over again. We're going to stop there because we've got all next week to finish up this chapter. So we're going to stop and let that marinate. I think the second part of this chapter is a little bit easier than the first. So we'll have more than enough time. We'll do some more practice with the gram to mole to gram next week when it's all just totally disappeared from your mind, because I'm sure that will happen. We'll do some more practice. But otherwise, you all have a really good weekend. Because of the structure of having 2 weeks for this specific chapter, because it is so dense, you won't have an assignment. You don't have a homework assignment due this Sunday. I do think you still have a lab though. So just check on dates. If you have any individual questions, feel free to stay around. Otherwise, I will see you next week. Don't forget to change your clocks. I think that's happening this weekend. So I will see you, I never know, an hour earlier or an hour later, something else. So bye guys.